The collision theory is a way of explaining how reactions happen. How do you get products from your reagents? The idea is when your reaction takes place, the chemical bonds in your reagents need to break and new bonds between atoms need to form, so you get the products. So for the reagents to make products, for the reactants to make products, their molecules must collide with each other, and they must do it effectively. The right atoms need to collide with each other, so the bonds that they have with their reagents are broken, and a new bond or bonds are formed. So that energy of the collision needs to be greater than the bond energy of the reagent. So it needs to be worth it for that bonds to break and the new one to form. The new one will only form if the collision is effective, and if that energy that is liberated is enough that it will break the bonds that those atoms have already with their own compounds, and to form the new bond. The more effective collisions you've got, the more likely are for those bonds from of the reagents to break and the new bonds to form, so you can get products. So what sort of things make those collisions more effective? What factors will influence reaction rates? Well, physical state and particle size. Gases, because they are more mobile, they have fewer intermolecular forces keeping them together, the different molecules of the product of the reagents. Actually, they don't have any. They are all separated. They move faster. They move, and they are more likely to collide. They are more likely to collide, and the more collisions, the more likely they are that some of them will be effective. The right atoms will collide with each other, and a new bond will be formed. Then liquid. In a liquid, you have some intermolecular forces. Those are the forces that keep the molecules, different molecules together. And then solid. So solid is the one that will have the worst reaction rates, because those molecules are quite tightly held together with each other in the different reagents. So they are less likely to collide with the molecules of the other reagent to make the product. And in the solid state, there are differences. If you have smaller particles, then that will give you a higher reaction rate, because you have finer particles, more surface area, more likelihood to, for example, if you have a solid and a liquid, or a solid and a gas reacting. If the solid is finely divided, you have more surface area exposed, and it will be easier for the molecules of the gas or the liquid to collide with the solid and form effective collisions that will give you the product. Typically, obviously not all the time, but when you increase concentration of the reagent, the rate increases, because you have more of both, and well, they will be more likely to collide with each other. In general, temperature helps the reaction rate. It's a bit tricky when you have an endothermic reaction, because those it's a bit tricky when you have an exothermic reactions, because those release heat. So actually, the fact that you are using heat on something that already releases heat, it can be a bit peculiar. But in general, temperature increases the reaction rate, and typically we calculate the rate doubles every 10 degrees. You have to be careful with the temperature, because if you increase it too much, your compounds might not be stable at those temperatures, so you have to be mindful with it. But yes, temperature increases the reaction rate because you are giving more kinetic energy to your molecules, especially if it's a gas. They move faster, they move more, they are more likely to collide with each other, you are more likely to have an effective collision. And the next step is the presence of a catalyst. A catalyst is a substance that is present in the reaction, but is not consumed. It's not a reagent. It's not a product. You add it, it enables the reaction to happen, but it does not get consumed. At the end of the reaction, you still have your catalyst. And that can have a huge influence in the reaction rate. And we'll talk more about it in the future slides. To understand the role of catalyst in increasing the reaction rates, in affecting reaction rates, we need to understand first what activation energy is. Activation energy is the minimum amount of energy needed for reagents to react, to undergo a chemical reaction. And you always have time. That first amount of energy, that minimum amount of energy that you need to get the reaction going, to get those collisions going, to get the reactions, the reagents collide, breaking bonds and making bonds. And you always have it. It doesn't matter if the reaction is endothermic, it doesn't matter if it's exothermic, releases heat about that initial burst of energy, you always have it. And catalysts act on that part, that activation energy. Let's have a look at how that might look like in a sort of graphical way. I'm going to ask you to stop the video and draw an energy diagram for this reaction. And we have done in previous videos. You have a reagent A that produces a product B, and this reaction has a delta G negative. So this reaction is spontaneous. So how would that energy diagram look? I'm going to just draw it so to get you started. So imagine here would be energy that I'm giving you delta G, free energy, and this would be reaction. And I'm going to put my reagent A. So if this reaction is spontaneous, delta G is negative, where would I put B? Would I put it lower than A? Do the products have less energy than the reagent, or would I put it higher? Have a think, stop the video, and see if you can come up with an answer. Stop the video now, please. Okay, so 50-50% chance that you got it right. Hopefully you put B lower. And this is the delta G for that reaction. Those reagents have enough energy to make the products without any help from the outside world and have some energy to spare. And that's what that means. That's what I put my reagents higher than my products in that energy diagram. It's not arbitrary units, but they are higher. They have sufficient energy, similar to when we were doing enthalpy diagrams. That reagent has enough energy to make the product and has some energy to spare, and that's what it releases. So what does activation energy is? Well, we call it typically EA. This. For the reaction to take place, it needs to start. Those first molecules of reagent need to start reacting. And so you always have that first initial burst of energy. You need your reagent not just sitting waiting for something to happen. You need it in what we call an activated state. And we put an asterisk next to the reagent, and we call this activated state. And how that activated state might look like very different depending on the reagent, it doesn't matter. You need some initial burst of energy for the reaction to happen. And then once you have that, then because the products have a lower energy than the reagent, the reaction goes without any additional help. And that is where a catalyst is going to act. It's going to help, a catalyst will act by finding an alternative path to reach that activated state that will be less energy intensive, so it will be easier to reach. In a similar way as the previous slide, I'm going to ask you now to draw another energy diagram for this reaction. And in this case, this reaction has a delta G, changing gives free energy positive. That means that the reaction is non-spontaneous. Doesn't mean that it's not going to happen. It means that it's not going to happen spontaneously. You want it to happen, you have to do something about it. So again, I'm going to draw my energy diagram as in a similar way. So here is the change in free energy, and here is how the reaction progresses. And again, I'm going to draw my reagent here. Where would I put the product? Would I put it at a higher energy level than the reagent, or would I put it to a lower energy level? Have a think about it, and pick an answer. Stop the video now, please. Okay, so hopefully you chose to put your products higher than the reagents. And that is what it means to have a non-spontaneous reaction. It means the reagents on their own, left to their own devices, do not have enough energy to make the products. If you want to make the products, you need to provide that energy difference to get the products. That's what we really mean when we talk about non-spontaneous. And in addition to, well, it's already non-spontaneous. If you need the reaction to happen, you need to provide a certain amount of energy. You need even more energy. A little bit more, or a lot more, depending on it is, because your reagents not only need a certain amount of energy to make the product, they need an additional initial amount of energy to reach that activated state. So activation energy happens both in a spontaneous and non-spontaneous reaction, in endothermic and exothermic reactions. It doesn't matter whether the reaction releases energy or absorbs energy. It does help in if the reaction is spontaneous, but even being spontaneous, you need an extra amount of energy to initiate the reaction, to reach that activated state, to get that reagent or reagents, to get those first collisions, and to the first collisions going, and those first bonds being broken, and other bonds being made. And that initial amount of energy, that minimum amount of energy you need to kickstart the reaction, is what we call activation energy. And you always have that. Doesn't matter whether the reaction is spontaneous or not. Even a spontaneous reaction, you still need that extra burst of energy to then make the products. And this activated state is where catalysts will act, and that's how they will help speed the reaction rate. They won't change the reaction. If it's endothermic, it's endothermic. If it's exothermic, it's exothermic. If it's spontaneous or non-spontaneous, they don't change that. The thermodynamics. What they do change is that activated state, that burst of energy that makes the reaction to happen.